Hi guys, welcome back to part 2 of integration by substitution. In this video I'll be solving 3 problems. 2 of them will be an indefinite integral and 1 will be a definite integral. So let's start with the 2 indefinite ones. So let's say we have the integral of sine x multiplied by e to the power of cosine x with respect to dx. What can we choose as our u value? So if we differentiate it, the derivative is already in the integral. Well, we can use cosine x because the derivative of cosine x is negative sine x, and we have a sine x in the integral, which means we'll be able to cancel. So let's rewrite this. We have sine x multiplied by e to the power of u minus du over sine x. The sine x's cancel out, but we still are left with a minus value, so we can just put that at the front of the integral. And then we are just left with e to the power of u du. There's no more x variables left, which means we can now evaluate this integral. So we get negative e to the power of u plus the constant of integration. And we always want to fill the u value in, so it's going to be negative e to the power of cosine x plus c. And that's the answer to this problem. So let's do one more indefinite integral. Let's say we have the integral of x multiplied by 3x squared minus 5 all to the power of 3 with respect to dx. Now, what tends to happen when we have something in brackets, that usually is the u value. So let's give that a go. So u equals 3x squared minus 5. The derivative of this, well, if we use the parallel, 2 times 3 is 6, x, 2 minus 1 is just 1, and then minus 5 is 0. So we have 6x as the derivative, and we have an x there and an x here, which means we'll be able to cancel, so we know this is the correct substitution. So we can rewrite this as x multiplied by u to the power of 3, and if we rearrange this, we get du over 6x, the x's cancel out. We are left with du over 6, which is the same as 1 over 6, so we plug that in at the front of the integral, and we're left with u to the power of 3 du. Since these are just u variables, we can now go and evaluate this integral. So it's just 1 over 6 multiplied by u to the power of 4 over 4 plus the constant of integration. If we simplify this now, we get u to the power of 4 over 24 plus c. And let's fill in what u is. U is 3x squared minus 5 to the power of 4 over 24 plus c. And that's the answer to this problem. So we'll do one more, and this will be a definite integral. So we'll need more space for this. Let's say we have the integral with the limits of 0 to pi over 4, and we have e to the power of tan x over cosine squared x with respect to dx. Now let's look for a u value that when we differentiate it, the derivative of that is in the integral. So let's say u equals tan x. The derivative of that is simply 1 over cosine squared x. We have a cosine squared x in the integral, which means this substitution is probably the right one. So if we rewrite this, we get e to the power of u over cosine squared x du over cosine squared x. These two cancel out, and we are just left with u variables. So we have e to the power of u with respect to du. But because we have changed the variable, we have to change the limits. So let's take the lower limit, and let's make that x in this u equals tan x. So u now equals tan 0. And make sure you have this in radians in your calculator, and if we evaluate it, it just becomes 0. If x equals pi over 4, then u equals tan pi over 4. This comes out as 1. So our new limits are 0 to 1, e to the power of u du. Now we can just simply evaluate this with the new limits. This becomes e to the power of u, 0 to 1, no constant of integration as it's a definite integral. And we just plug these values into u, so we have e to the power of 1 minus e to the power of 0. And anything to the power of 0 is always 1, so the final answer is e minus 1. And that is how you do a definite integral. So the steps are very similar. It just has an extra step basically. You have to change the limits when you change the variable. So that's it for this video, guys. I'll post another one on substitution tomorrow.